All right. I believe we are live on YouTube. Okay, so this recitation, we're going to go through a bunch of proofs and different proof techniques. Quiz number 2 is going to be in 2 weeks, and
All right.
and it's going to be on proofs.
I believe we are live on YouTube. Okay, so.
All right, I'm having my YouTube playback as well. All right, so a few announcements. There was a major problem last week. Everybody survived it. We have a bunch of power and internet outages. So we have been fairly accommodating for quiz number 1, but I sent out an announcement yesterday. For quiz number 2, we are going to try to follow our actual rules for those exams. So most important part is that if you have not read about the course syllabus and the various instructions, please do so as soon as possible. Will not be as accommodating for quiz 2 as we have been for quiz number 1, because we know that the power outage has caused a lot of disruptions. But for quiz number 2 and all the following exams, it's important to mention that you should always submit your solutions through Gradescope. The only exception we will make for sort of accommodation is going to be related to documented emergency, for example, documented medical emergency. And we will not allow emailed solutions. You have to use Gradescope. If you end up having a power outage or any sort of outage, that the only thing we will ask is actually a documented emergency that it can be sent from your power or internet company, and we will not accept any other reasons. And if your internet at home is indeed unreliable, you should come up with a backup plan, especially for exams and quizzes. Okay, one thing that we did make a change is we extended the grace period from 15 minutes to 30 minutes. So in a sense, by the time you start your quiz, you have essentially 90 minutes to submit. However, you should consider using the last 30 minutes really as the time spent to try to figure out the submission. Do not use that to do problem solving, because some of you have experienced that where you leave like the last 2 minutes for submission and you will not be able to submit on time. So please use that 30 minutes time wisely. Try to reserve that for submission purpose only. Okay. And again, please read the syllabus and various instructions on homework submission and quiz submissions ahead of time. And also lastly, please make sure you know how to submit your solutions through Gradescope. By default, Gradescope accepts one single PDF. So if you do not know how to combine multiple PDF into a single PDF, if you do not know how to sign your pledge page, all those technical difficulty you have had for quiz number 1, please go to TIA office hours and try to learn how to do this properly. Online, I have also posted information of how to sign pledge page using Adobe Online, and this is a free service to all University of Utah students. So that will be one option for you to sign your pledge page. Okay. So please make sure before quiz number 2 that everything is actually working on your end, especially in terms of submission. We will not accept any technical reasons if you cannot figure out how to use Gradescope for quiz submissions in the future. Okay. So a few announcements. Your homework 1 has been graded. Thanks for all the TAs who work really hard. Some of them actually also lost power and internet for a few days. Based on our syllabus, once you have received your homework grades and also your quiz grades on Gradescope, you have 1 week of time to request any regrading requests you might have. The second announcement is that homework 2 is due this Friday at midnight. So make sure if you have not started, start them today for homework number 2. And homework number 2 is on proofs, which is the focus of quiz number 2. Okay, and For quiz number 2, one more thing I want to emphasize, historically, students find the quiz number 2 to be the hardest. So you should prepare accordingly. Again, if you're having trouble understanding understanding proofs and so on, please go to office hours. And there's various ways to get help. Of course, you can always post under Piazza, under different folders for homework and for quiz. You should go to office hours. There's also information I posted on Canvas, which is we have School of Computing have those tutoring center. Specifically for 2100, they have, I think, roughly daily availabilities for one-on-one help at the tutoring center. And also, you are allowed to have a virtual study group, but you should be mindful about our cheating policy. You should read about our cheating policy before you form those study groups. Okay. All right, any questions so far? Okay, if there's no questions, let's dive into proofs. Okay, so I would like you to use the property of integer division to prove the following proposition. Okay, if 9 divides 10 to the power of n minus 1 minus 1, then 9 divides 10 to the power of n minus 1. Okay, where of course, let's say n here is bigger or equal to, let's say, 1. Okay. All right, so you have 2 minutes to sketch a proof, and we'll start now. Okay, so while you're thinking about the proof, there is one property this is going to use. For example, if I assume, let's say, in this case, both A and B, let's say positive integers. Well, integer is actually fine. Let's just say they are integers. And then if A divides B, that means B is divisible by A. That means B is equal to K times A for some K that's integer. Okay. So in this case, while you are thinking about this problem, we have 2 points here. One is you're looking at what is a property when a number 9 divides an integer. What is a property associated with that? So as you are thinking about the sketch of the proof, by following this property here, if 9 divides some integer, let's say m, then that implies m is equal to 9 times k for some integer k, right? So that is sort of the property you're going to use. In fact, you're going to use this property several times for the proof. Okay. Later in this lecture, we're also going to go over a similar problems where instead of asking for a direct proof, I'm going to ask you for induction proof. So again, it's going to use a similar set of properties. Okay, so time is up. Do I have a volunteer to tell me what is the main idea behind this proof? Do I have anyone? You can raise your hand, or you can type in the chat window. All right, if there's no volunteers, that we're going to do it together, okay? Don't be shy. We're going to try to solve this together. So, okay. So the sketch, what I'm going to use here is called direct proof. And of course, I'm going to use a property I just reviewed, okay? So the first part of this is my hypothesis. The second part is my conclusion, okay? So by the definition of integer division, using the hypothesis, because 9 divides 10 to the power of n minus 1 minus 1. That means 10 to the power of n minus 1 is equal to 9 times k for some k is part of integer. This is just a direct translation of the hypothesis statement, okay? So now if you look at what is my target is I need to arrive at 10 to the power of n minus 1. So obviously the next thing I need to do is I need to do some algebraic manipulations, okay? So this is really the most, to some sense, the hardest part. I know the form for 10 to the power of n minus 1, and I need to arrive at something that is 10 to the power of n. So another property that you're going to use is, x to the power of a times x power of b is x to the power of a plus b, right? This is, again, a rule in basic algebra. So in this case, I can think about 10 to the power of n is 10 to the power of n minus 1 times 10, okay? So this is a relation between these two terms that I'm after. So in this case, once I have this form here, I'm going to multiply 10 on both sides. So I have 10 times 10 to the n minus 1 is 9k times 10, okay? And I sort of open up the parentheses. I have 10 to the power of n minus 10 on the left-hand side. On the right-hand side, I have 90k. Now the next thing, remember my target is 10 to the power of n minus 1. What I can do is, in order to create minus 1 on the left-hand side, I'm going to add 9 on both sides. So I have minus 10 plus 9 is equal to 90k plus 9, okay? So if I simplify, I have 10 to the power of n minus 1 is equal to 9 times 10k plus 1, okay? And then since this is sketch, I'm going to say it here. By closure property of integer under multiplication and addition, okay? 10k plus 1, let me name it to be, let's say m, is 10k minus plus 1. This is an integer. So that means 10 to the power of n minus 1 is now equal to 9 times some integer, okay? So that means 9 divides this number, okay? So if I go back to the proof, what are the property I'm using? I'm using some algebra manipulation, and I'm using the property of integer division, okay? Any questions? Okay, if there's no questions, let's move on to the next problem.
I have a question.
Yes,
Sorry.
go ahead.
Just in the last part, the algebra that you do for separating the 10 to the n minus 1, and you get 10, why didn't you get 10 to the n times 10 to the minus 1?
Which step is okay, so there's the first step, multiply by 10 and open up the parentheses, right? And the next step, I add 9. So which step are we talking about here?
So you have 10, so you have 10 to the n minus 1 minus 1.
Yep.
And you change that to 10 to the n times 10 to the minus 1? And then divide out
from
the
this
10.
Okay, let me use blue. So you're saying from this steps to this step, how do I get there?
No, where did the 10 come from? Because the way I see the rule, x to the a times x to the b, you get x to the a plus b, and since you have n minus 1, wouldn't it be 10 to the n times 10 to the minus 1?
So yeah, so actually let's do this. If I want to use this exactly letter to the letter, so 10 is 10 to the power of 1, right? 10 is 10 to the power of 1.
Yes.
And then 10 to the n minus 1, if those two multiply, this is equal to 10 to the 1 plus n minus 1, which is 10 to the power of n. Is this clear?
I just don't know why that works.
So
why can we add a 10?
No. So think about this. This is this rule right here, what I wrote here. This rule is, if I actually expand this, I'm going to use blue. Oh, sorry. I'm going to use green, right? So what is x to the power of a? X to the power of a is a copy of x multiplied together, right? Is this clear? This is by definition of a power. If you take a number to the power, this is a copy of x multiplied together. Now, x to the power of b is similarly b copies of x multiplied together. Let me use cross. They're multiplied together. Now, x of a plus b is what? A plus b copies of them multiplied together.
Yes.
Okay. So there is total of a plus b copy. Okay.
Yes.
So now if you look at this, if I take the first part, which is a copy of x times b copy of x, total, I have a plus b copies of x multiplying together. That is the sort of the logic behind this formula.
Yes.
Okay. All right. I think one more person, Jake, you raise your hand. Go ahead.
Yeah, just going into this, I was wondering this the line that comes after 9 in the proposition, what does that mean? That's kind of what tripped me up.
Oh yeah, this is division. So
that's division. Okay.
Yeah. So if a, like I say, if a divides b, that means b is equal to a times some k for some integer k. For example, I would say 2 divide 6, right? So that means 6 is divisible by 2. Similarly, 3 divide 6. That means 6 is divisible by 3, right? And then, for example, 5 divides 15. That means 15 is divisible by 5.
Okay,
That's what this symbol means. Okay.
Thank you.
Another way to think about it, actually equivalently, is when a divide b. That means when b mod a, its remainder is 0. That means it's divisible by a. Okay. So this is basically, that means b is divisible by a. Okay. All right. Let's move on to the next one. Now this similar things come up. This means the statement is if a divides b and a divides c, then a squared divides b times c. Again, a divided by b means that b is divisible by a. A divides c means c is divisible by a, and so on and so forth. So you're going to use the same. Sort of philosophy as before. If a number a divides b, that means b is some integer multiply of a, as before.
There's a question in the chat real quick.
Yeah.
If we can go a little bit slower on this next proof.
Sure. Yeah. We can go over slowly. So you have, I will give roughly 40 seconds to think about if you were going to solve this problem, what is the first line of attack, right? I kind of give you a hint already. If a divides b, that means b is a multiply of a with an integer. So in this case, you need to take advantage of the problem statement. A divides b, what does that mean? A divides c, what does that mean? And then what it means for the conclusion, which is when a squared divides b times c. And to give you a hint, again, we're going to use essentially direct proof. And also we're going to use property of integer, that is closure under multiplications. Okay. And then one more thing, if you want to put this particular statement into context, I can give you an example, but this is not, keep in mind what I'm giving you an example is not a proof, right? This is just validate this particular statement. For example, I can consider 3 divides 6 and 3 divides 9. Then what this means is 3 squared divides 6 times 9. What does that mean? That means that is 9 divides 54. That's sort of one application of this proposition. Okay, of course, you can see many other examples. All right, do I have a volunteer? What is the sketch of this proof?
First, you can say that B equals K times A, and then that C equals L times A.
Great.
And K and L are both integers.
Okay, great. That is really the high level picture of this proof. Thank you very much. But let's do it slowly, right? So by the hypothesis and integer division, because A divides B, that is part of the hypothesis, that means B is equal to, I guess you're using A times K, right? For some K that's integer.
Yeah.
Right. Yeah, thank you. And also A divides C means that C is equal to A times L for some integer L. Right? So both of this are just using the property of integer division, which means that, you know, if B is divisible by A, then B is some copies of A, some integer copies of A. And if A divided by C means C is divisible by A, which means C is A times some integer. So C is equal to L copies, some number of copies of A, right? That's what division means. Okay. So now I'm going to do what is B and C mean. So because I'm define B is equal to A times K, C is equal to A times L, then basically by substitution, A times C is now, B times C is now AK times AL, okay? Which is A square times K times L, which is A square parenthesis K of L, okay? So everything I've done so far is some algebra. And the last bit is I need to prove that KL is integer, right? If KL is integer, then BC is an integer copy of A square, integer number of copy of A square, which means A square divides BC, or BC is divisible by A square, okay? So now what I do is by closure property of integer under multiplication, I let an integer P is times K of L. By closure property, this is integer. Therefore, BC is A squared times some integer. And again, by definition, this means BC divides A squared. And that's the end of the proof. Okay. So if we go back to this proof, what are the key properties? Because A divides by B, B can be expressed by K copies of A, so K times A. Because A divided by C, C equal to A times L, so L copies of A. And finally, I want to prove A squared divides BC. That means eventually I want to arrive at the conclusion where BC is equal to A squared times some integer. Okay, so that's it. All right, Ashton. Is it Ashton?
Yes.
Yeah.
So I'm just wondering, why are we using AB and AC? Why not? I guess I'm just kind of lost as to why how AB, that means that B equals A of K, and then AC means that C equals A of L. I'm just kind of lost on that part.
Okay, so again, this is a definition of integer division, right? If A divides B, this symbol here means that A is a factor of b. Okay, so if I use, instead of using variables, let me use actual integers. So when this symbol really means b is divisible by a. Okay, so for example, 6 is equal to 2 times 3. 6 is divisible by 2, and 6 is also divisible by 3. What does that mean? If I take 6 and I divide by 2, I arrive as another integer, right? That's what it means by divisible. When 6 is divisible by 3, that means if I take 6 divided by 3 is equal to 2, right? There's no remainder. So another way, by definition, an integer is divisible by another integer is this integer can be expressed as a multiplication of the other integer times integer. So again, the definition is if b is divisible by a, then b can be factored into some integer times a. That is divisible mean as a definition.
Okay, and so we can do
I
anything for a divided by c.
Yeah. So so for example, if b is divisible by a, that means b is some integer times a. For example, 6 is divisible by 2, that means 6 can be expressed by 6 is equal to 2 times some integer.
I have a question.
Yeah.
Shouldn't the last part be a squared divides bc instead of the other way around?
Oh yeah, you are great. Thank you. That's a typo on my end. That means you are paying attention. Thanks very much.
Sorry, I just realized I'm not set as co-host, so I can't put hands down. Would you hurry in?
Oh, sure.
Sorry, I
Yeah.
just barely realized.
Let me do that. I'm just trying to find your name. All right. Okay, now you're a co-host. Okay. All right, any more questions? All right, let's move on. So now I want you to prove by contradiction, right? So if you think about all the proof technique you've seen so far, we have direct proof, we have proof by contradiction, we have proof by cases, and we have induction proof, okay? So I hope we have enough time to go through at least one induction proof today, but let's first do proof by contradiction. So it says if A is a rational number and B is irrational number, then A plus B is irrational, okay? Let's say I'm using Q to represent the set of rational number, Q prime to represent the set of irrational number, okay? So again, I want you to start thinking about if you were going to prove this by contradiction, what would you do, okay? But while you're thinking about it, let me remind you the definition of a number to be a rational number. Okay, a number, recall a number, let's say X, or maybe let's say, let me use A instead. A number A is a rational number if it can be expressed as X divided by Y, where both X, Y are integers, okay? For example, the number 2/5 is a rational number because this is expressed as integer, as 2 divides 5, okay? So that's a rational number. So that is a property you're going to use. And while you think about it, the other thing you want to recall yourself is what is mean by proof by contradiction. If I have a particular statement, I want to assume there's a counterexample. And the counterexample is essentially, if I have statement P implies Q, you want to look for the counterexample that is P, but not Q. This is really at the center of thinking about a counterexample. So do I have a volunteer to tell me what, if I were going to assume a counterexample exists, what is the condition on this counterexample?
So the hypothesis would need to be correct?
Yes, you use a hypothesis and then you kind of take the negation of the conclusion. Okay. So do you have an idea what this counterexample looks like?
So, oh, you got you know in the comments.
You go ahead.
All right. So I guess if A is a rational number, and then if B is a rational number, and then we want to,
Irrational, right? Irrational. So we don't change hypothesis. Yeah. And
then we want to find that A plus B is rational. And
yes,
come to the
exactly.
contradiction.
So this is exactly, this part here is P, statement P. This part here is not Q, right? Because P, let me use a different color. So statement P is, let me put it right here. Statement P in this problem is A is rational number and B is irrational number, right? That's P. And then conclusion Q is A plus B is irrational. So if I want to do P and not Q, this is this statement. Okay. So what is this? This is to say that assume exist a counter example. And what is this counter example? That the counter example is A is rational, B is irrational, but A plus B is rational. Once you assume there's a counterexample, you want to prove that if a counterexample like this exists, it will lead to a contradiction. Okay, which means counterexample does not exist, which means the original statement is true. So what you want to show is you want to show such a counterexample does not exist. That is really the idea behind it. Okay, but for the time being, I'm going to assume a counterexample exists. Okay, do I have a volunteer of what the next steps might be?
List A as being one integer divided by another.
Yeah, let's say x, y, right? This is by definition because A is rational. Okay, yeah, keep going. What is the next step?
That's all I got.
Okay, that's a good start, right? So remember, when I say there's a counterexample exists, that means A is rational and A plus B is also rational. So by definition of rational number, so this is by definition of rational number, because A is rational, A is x divided by y, where x, y are integer, but also because A plus 1 is a rational number, so A plus 1 is equal to m divided by n for some integer m and n. This is just using definition of something being rational, okay? And then the next step, of course, is to prove that.
I got a question real quick. Ashton, go ahead.
Yeah.
So yeah, aren't we trying to find that A plus B is irrational?
Yes, but I'm trying to prove by contradiction. Proving by contradiction is assume there exists a counterexample, where the counterexample means that A plus B, A is rational, B is irrational, but A plus P is rational. So this is a condition of a counterexample is P and not Q. So I'm assuming a counterexample like this exists and then prove there's a contradiction.
So could we do something like similar to like how it was on lecture 6 quiz, to where we set up the table and go through like A is rational, B is rational, and so forth? Or is that not?
I think that's going to be challenging, because one thing that is really challenging about any proof involving proving something is irrational is directly proving something is irrational is much harder than proving something is rational. Because the definition of something being rational is that there exist integers so that it can be represented as two integer division. But if it's something irrational, directly proving something is irrational, it's going to be very hard. And also in some instances, the proof can be done using a truth table. But I think for this particular problem, if you try to prove it by truth table, it's going to be very challenging. That's why we're trying to prove by contradiction. Okay. Another thing you can prove actually is you can also try to prove this. If you think about this as a take home, you can also see if you can prove this by contrapositive statement, but that is a different type of proof. Okay. But here I want to prove by contradiction. So if in the quiz, if I'm specified proving by contradiction, I really want you to use this kind of proof techniques. Okay. All right. So going back to the problem, because
One more question,
Yes.
Jackson.
Yeah, go ahead.
Let's see. Jackson, you're muted still.
Is there a definition for irrational number that we need to use? Because I mean, that's what I want to do, but I can't
Well-
think of a way to define what an irrational number is
Okay.
other than it's not a fraction, not able to be represented by
No.
a fraction.
Actually, what you just said is exactly the definition of irrational number. A
Yeah.
number is irrational if it's not rational.
But how do you turn that into math symbols?
That's exactly what the challenge. You don't have that definition, right?
Yeah.
Now, so the definition of a number be irrational is that if it is not rational, that means it cannot be expressed by two integers divided by one another. Okay, so that's why it's challenging, because it does not have a very good mathematical formulation directly to define what is a number to be irrational. Okay, all right.
Okay.
So now let's look at this, right? So because I assume there's a counterexample where A is rational and A plus B is rational. Now I can solve for B, okay? So B is going to be M divided by N minus A, right? This is just by definition. And because A is X over Y, so it's going to be M over N divided minus X over Y. Now I'm going to do, again, algebra. I'm going to do, this is equal to N times Y, M times Y, minus N times X, okay? So this is the algebra formula here. A minus B minus C over D is equal to BD of AD minus BC. This is a formula from basic algebra. So now the next thing I'm going to use is basically closure property of integers. What is this property? The top part is integer multiplication and integer subtraction. The bottom part is integer multiplication. So again, I'm going to use closure properties of integers, means that it's closed under multiplication, subtraction, and addition. So again, by the closure property of integer, I can let the top to be my minus nx, which is p. This is integer. The bottom is n times y, which is also integer. So now b is equal to p over q. What does this mean? That means b is equal to two integer, can be expressed as two integer divides one another. Now this means that b is rational number, right? This is by definition because it can be expressed as an integer on top and an integer on bottom. So what does this mean? This created a contradiction because we assume that b is irrational, but somehow I arrive at the conclusion that b is rational. So this is a contradiction. So this is a contradiction. So when you assume a counterexample exists, that leads to a contradiction, which means that counterexample does not exist, which means the original statement is true. Okay. So that is proving by contradiction. All right. Hopefully we have time to do one more. This is induction, and I have to warn you, this is not an easy problem. So I will give you 2 minutes to start thinking about this problem. And this is by induction, and historically induction is one of those hardest proof techniques. But once you get used to it, it's really boiled down to 4 steps, okay? There's usually a problem statement step. There is an induction hypothesis step. Well, actually, sorry, before that, there is a base case. And then there's induction hypothesis, and then there's induction step. Those are usually the 4 steps of induction proof. So my hint to you is to think about how do I make a statement? What is my statement? What is the base case? And what is the induction hypothesis? And what is induction step? And while you're looking at this formula is a summation of a number sequence. And if you're unfamiliar with this, again, I will encourage you to review a bunch of algebra concepts. So what this formula means, this means I'm going to have a bunch of terms added together where the first term is replacing I by 1. So the first term of this sum is 1 over 1 times 2. The second term of this summation is 1 over, now replacing I by 2. 2 times 2 plus 1, which is 3. And then this next term is replacing I by 3, is 1 over 3 times 3 plus 1, which is 4. And then the last term is replacing I by n, which is 1 over n times n plus 1. And what this statement is asking is want to ask you that if I have all these terms summed together is equal to the right-hand side, okay? So do I have anyone who can give me a problem statement?
Isn't it just the statement they have written up there that these two are equal?
Yeah, but I want to, yes, that's correct. But I want to make the statement where I want to use P of n to represent the statement. The P of n means that when exactly for I is equal to 1 over n, okay? So it's not different from you. I just put a symbol. This symbol P of n represents this entire equality, okay? Now, what is the base case? Because n is bigger or equal to 1, right? So what is the base case?
In the chat, we've got a few answers.
Sure.
P of 1 equals 1/2.
Oh, okay. I need to make a differentiation. My statement P of n is a whole statement. This is just a P of n represent the statement of this inequality. It doesn't mean the left-hand side. So similarly, what I want to show is want to show P of 1 is true, meaning that the statement is true when n is equal to 1, right? Which is exactly what you typed here. I want to show when n is equal to 1, the statement is true. That means I have the term on the left-hand side. I have just one term, 1 over 1 times 1 plus 1, which is 1 over 1 times 2, which is 1 over, on the right-hand side, 1 plus 1, which is 1 over 2. This is the right-hand side, this is left-hand side. So to show P of 1 is true, that really means if I just want to put the summation formula, this is really I is equal to 1 to 1 of I, well, let me rewrite it. This is say I is equal to 1 to 1, right? 1 over I times I plus 1. So this is a summation, but they only have one single term. And this one single term is 1 times 1 plus 1, which is 1 over 2. And then on the right-hand side, I have 1 over 1 plus 1 is 1 over 2. So my left-hand side is equal to the right-hand side. So this statement is true, or this equation is true, okay? What is my induction hypothesis? Anyone?
In the chat, P of n holds.
Yep. So assume P of n is true, but of course, let me spell it out. P of n really is the statement I from 1 to n, 1 over I times I plus 1 is equal to n plus 1. Okay, what is induction step then? Is we want to show? What do you want to show?
In the chat, we've got P of n plus 1.
Yep, we want to show P of n plus 1 is true. Of course, because it's an induction proof, we always have to make use of induction hypothesis, right? Okay, do we have a volunteer for the last step? How do we get to the final proof? We need to make use of induction hypothesis which is what we assume. So we need to use this algebraically. Anyone?
It looks like in the chat there's an answer. I'm not sure I'm reading it right. That says replace L equals n plus 1.
Okay, I think I know what this means. So what is p n plus 1? A p of n plus 1 on the left-hand side, I need to have a summation I from 1 to n plus 1. So instead of having n terms, I have n plus 1 terms. And I have I times I plus 1. This is the left-hand side. But what I'm going to do is the left-hand side can be decomposed into two terms. First, I can do a summation of the first n terms. And then I can add the last term. Right? So this is using the formulation where the left-hand side of this equation, I'm summing n plus 1 terms. And I'm going to separate the first n terms because I want to use induction hypothesis plus the last term. And now because I'm using induction hypothesis, so here is what I'm using induction hypothesis. We have this left-hand side now is equal to n plus 1 plus 1 over n plus 1, n plus 2. Okay? And then the rest of it is just algebraic manipulations. Okay? So what do? I want to simplify this. I can have this is equal to n plus 1 times n plus 2 times n plus 2 plus 1. Because I take the first term, I multiply n plus 2 on both top and bottom. Okay? And now I further simplify. Sorry, I'm running slow in space. Did I add more space? No, I didn't. I have the top part is n squared plus 2n plus 1. The bottom part is n plus 1 times n plus 2. If you recall, we have the property a plus b squared is equal to a squared plus b squared plus 2ab. I'm going to use this formula in here where n squared plus 2n plus 1 now equal to n plus 1 squared over n plus 1, n plus 2. Cancel out one copy of n plus 1. We get n plus 1 over n plus 2. That's exactly the right-hand side for the statement p of n plus 1. That's the end of the proof. Okay? So really, the most tricky part of this question is this last bit of algebraic manipulation. When I use induction hypothesis, I got this term to add together, and I need to do some simplification to arrive at the final formula. Okay, so that is the end of the proof. Okay, so any questions so far?
In the chat, for induction, how do you know if you would use n minus 1 or n plus 1?
So actually, induction proof, you can always use two types of scenario. Let me just use the space in this page. So usually you have base case, right? Base case in most cases is you starting with 0 or starting with 1, but you know there's different base cases. But then in induction hypothesis, so if your base case is say p of 0 or p of 1, in the induction hypothesis, you can assume P of n is true. Then induction statement, you want to show P of n plus 1 is true. Okay? Alternatively, in induction hypothesis, you want to assume P of n minus 1 is true. And in induction step, you want to show P of n is true. Okay, so both you can achieve the final induction proof. In certain cases, the first one is slightly easier than the second one. And in certain cases, the second one is slightly easier than the first one. But if you want to do induction proof, you can do one of those two forms. For example, if you want to challenge yourself, you can in fact try to prove this problem by assuming P of n minus 1 is true and prove n is true. The proof techniques is actually fairly similar.
All right, and then Jake, go ahead with your question.
Yeah, so I'm a little confused how n plus 1 over n plus 2 proves the problem statement or the hypothesis. I don't understand how that proves it.
So first of all, do you understand induction hypothesis? Induction hypothesis is assuming when my variable is n, the equation holds. Do you understand this piece? Yes, okay. Now the next thing is, whenever I'm assuming n is true, I want to assume that statement, I want to prove the statement n plus 1 is true. So if you look at this statement here, I'm going to steal the next page space. The statement is I is equal to 1 to n of 1 over I times I plus 1, right? This is the left-hand side when I have n copies. But if I have n plus 1 copies, what is the statement I need to prove? The statement at n plus 1 is I want to prove when this number is now n plus 1, my summation is substituting the thing on the right-hand side, substitute n by n plus 1. So I want to prove n plus 1 plus n plus 1 plus 1, which is n plus 1 over n plus 2. So this is a statement I need to prove when I substitute the variable n by n plus 1. So the substitution happened both on the left-hand side and on the right-hand side. So this is what I want to prove. So then the rest of the things I did in the proof sketch is because I need to prove, let me use a different color. I want to prove this green statement is equal to this green thing. And every step in between is taking advantage of the formula from induction hypothesis. Okay, so the part that you need to get yourself familiarized with is how does a formula like this looks like if I replace the variable n by n plus 1. You need to replace n on the left-hand side by n plus 1. So we had one extra term. And on the right-hand side, the top becomes n plus 1. The bottom becomes n plus 1, which is n plus 2. So n is a variable that is substituted or replaced by n plus 1.
Okay, thank you.
All right. Okay, so we ran out of time. We actually have still 2 or 3 problems towards the end. What I would suggest you to do is try to solve it on your own. And if you have trouble, please come to the office hour. But I want you to try it first. Okay. All right. Again, thanks for the lecture today. And the quiz number 2 is coming in 2 weeks. And it's going to be on proofs. Okay.
Thank you.
Thank you.
All right, and then someone in the chat is asking if it's possible to do a breakout room to ask a short question about homework 2 after class.
Hold on one second.